Welcome to the Deep Dive, where we take your most challenging, often philosophical questions, filter them through rigorous science, and give you the knowledge you need to feel genuinely informed about the universe.
Today, we are tackling a question that sits right at the intersection of our deepest existential anxieties and our most rigid physical laws.
It really does. It's the ultimate, almost childlike query that nonetheless stumps most adults. Where does energy actually go when a complex system ends?
Exactly. I mean, what really happens?
That's the anchor of this deep dive. Our listener shared a fascinating stack of sources that zeroes in on two profound, really visible cessations. A roaring campfire that suddenly extinguished and, well, far more personally, the end of a human life.
It's that universal, what did I just witness vanish feeling.
Yes.
When we observe something as dynamic and concentrated as a flame or a living, thinking organism suddenly stop, our immediate human perception tells us that a massive quantity of energy has just ceased to exist.
It feels like a fundamental loss.
Or even a kind of physical magic, like a switch was flipped and it's just gone.
Our mission today is to strip away that feeling entirely. We want to move this from being a mysterious disappearance to a thoroughly predictable, observable, and scientifically factual transformation.
And the sources we have compiled provide a remarkably detailed roadmap for applying high-level physics to these intensely personal, everyday scenarios.
So we can give you the essential truth immediately, can't we?
Oh, absolutely. The energy does not vanish. It transforms. The entire analysis is governed by the single most important principle in physics, one that is completely non-negotiable.
The law of conservation of energy?
That's the one. This law is the shortcut to understanding that nothing is truly lost. It is simply accounted for, or as we're going to discuss, dispersed somewhere else.
Okay, let's unpack this universal principle, the law of conservation of energy, or LCE, because it is the bedrock for everything we're going to discuss today.
It really is.
The definition itself seems simple, but the ramifications, especially in these real-world scenarios, they're just astonishing.
The pure definition is, as you said, pretty straightforward. Energy cannot be created or destroyed. It can only transform from one form, like chemical, into another, like thermal or kinetic.
And this has to happen within a closed system, right?
Crucially, yes. It must hold true within a closed system. And for the vast majority of our discussion, the universe itself, or at least our immediate environment, functions as that system. The total energy quantity available remains constant perpetually.
What's so remarkable is how this concept seems to counter our daily experience. When we run out of gas in the car, or a battery dies, or a fire goes out, it really feels like the energy is just annihilated.
You do.
So why do we as humans struggle so much to accept this idea of constant mandatory persistence?
That struggle is deeply rooted in the second law of thermodynamics, specifically the concept of entropy.
Okay.
The LCE, the first law, tells us the quantity of energy is conserved. But the second law tells us that the quality of that energy is constantly degrading.
Wait, let's pause right there, because this is the critical distinction that really elevates the conversation. We have to introduce the concept of exergy versus anergy.
Absolutely. This is the whole ballgame. The perception of loss we feel when a fire stops is not a violation of the LCE at all. It's a consequence of the second law.
So what's exergy?
Exergy is the good stuff. It's the usable, highly concentrated energy, like the chemical energy locked in a log, or the electrical energy in a battery, or, the potential energy stored in a complex organism. This is the energy that can do work.
And anergy?
Energy is the useless, dispersed, low-grade energy. Think primarily of ambient heat, which is so spread out it can't be harnessed effectively anymore. It's still there, but its usefulness is gone.
So when the fire goes out, the total quantity of energy, that's the LCE, remains exactly the same. But almost all the exergy, that concentrated chemical energy, has rapidly converted into anergy.
Into low-grade thermal energy, radiated throughout the room or the atmosphere. Precisely. The energy hasn't vanished. It's just become useless to us.
I like the analogy one of the sources used. It's like taking a beautifully structured palace. That's your exergy.
Right, a very ordered, useful structure.
And then scattering its stones across an entire continent. That's the anergy.
Perfect analogy.
Yeah.
The mass of the stones is conserved, but the structure, the ability to use it as a palace, is gone forever. This explains that tricky feeling of the LCE. We're not seeing loss of energy, we're seeing loss of order.
That reframes the entire conversation. We're not asking where the energy went, we're asking where the usefulness went.
And the usefulness always goes into dispersal. It always spreads out. To help visualize this relentless, mandated flow, the sources use that fantastic metaphor of the river.
Right. Energy just flows onward like a river. It might change states from, say, a raging waterfall, which is high exergy,
A lot of useful directed power there.
to a sluggish, wide delta, that would be low exergy, high energy, or even from liquid to vapor or ice. But the total quantity of water, the H2O, never ceases to exist.
It's always moving, always cycling, always present, just changing direction or form. It cannot reach a dead end. The universe doesn't have dead ends for energy.
And to connect this more abstract flow to something modern, something we all get, we can use the analogy attributed to Richard Feynman.
The money exchange. I love this one.
It's so good. Energy is like money.
Right. Let's say you have $1,000.
Oh.
That's your conserved energy inventory. That amount is fixed.
You can exchange it for different currencies, right? Heat, light, motion, potential energy. But you cannot change the total balance in your universal bank account.
Not 1 cent. If you convert chemical potential energy, let's call that a $500 bond, into kinetic energy, a pile of $50, $10 bills, and some thermal energy, maybe $501 bills.
Your total is still $1,000.
The total remains $1,000. The analogy is perfect for bridging that gap in our perception. If a system loses 20 units of chemical energy, the universe has simultaneously gained 20 units in some other combination: heat, pressure, movement. It's a relentless, perfect system of universal bookkeeping that must always, always balance.
But if it's such a perfect, relentless system of bookkeeping, what are the biggest line items we consistently fail to account for? You know, when we're tracking these complex systems in our heads, where does the average person miss the exchange?
We miss the transfers that are invisible to the eye and undetectable by touch. When we look at a complex chemical system like the body or a fire, we often forget 3 major transfer types.
Okay, what are they?
First, latent heat. That's the energy required to change the state of matter, like boiling water into steam. You put a ton of energy in, but the temperature doesn't go up. That energy is hiding in the phase change.
Okay, that makes sense. It's not hotter, but it's holding more energy.
Exactly. Second is vibrational energy. This is the kinetic energy in the molecular bonds themselves. We feel this as temperature, but we often don't register it as energy in the same way we do a flame. It's the jiggling of atoms.
And then the third, you said it's the most elusive.
I think it is. It's the energy stored in the chemical bonds of waste products, things like carbon monoxide or methane. They're invisible gases, but they're packed with significant potential energy that hasn't been released yet.
So the feeling of magic is simply sensory deprivation. We stop seeing the concentrated light and heat of the flame, but the total movement of the atoms, that kinetic energy, is still there. It's just diffused across a much larger volume.
That's it exactly. And the crucial element that ensures this is not philosophical musing, but cold, hard fact, is its mathematical foundation. This is where we have to bring in the towering figure of Emmy Noether.
Her contribution is it's so fundamental, and it gives the law of conservation of energy the immense scientific authority it deserves. It wasn't just observed, it was mathematically proven to be a necessity of the universe.
It's an incredible story. Noether, who is often undercredited in popular history, proved in 1915 that for every continuous symmetry in the laws of physics, there must be a corresponding conservation law. This insight, known as Noether's theorem, tied the highest level of abstract mathematics directly to physical reality.
So let's clarify that for our listener. What does continuous symmetry even mean in this context?
It's a great question. The most direct symmetry relevant here is time symmetry. Put simply, time symmetry means that the fundamental laws of physics are the same today as they were yesterday, and they will be the same tomorrow.
So like gravity works the same way on Tuesday as it does on Saturday.
Exactly. If you run a ballistics experiment right now, and then you run the exact same experiment 1 hour later, the laws governing the trajectory of that ball have not changed one bit. The universe doesn't care what time it is.
And the only way that the universe behaves consistently over time can be mathematically true.
The only way that consistency, that symmetry across time is guaranteed is if the total energy inventory remains the same throughout that shift.
Whoa.
Think about it. If energy could spontaneously appear out of nowhere or just vanish, the fundamental laws would have to change over time to account for it. Time symmetry would be broken. So because the universe operates consistently, energy must be conserved. It's a logical necessity.
That is a staggering realization. The conservation of energy isn't just a rule, it's built into the very consistent behavior of the universe itself. If the LCE failed, all bets are off. Time travel might be possible, or the laws of gravity might suddenly reverse themselves.
You've hit the nail on the head. It guarantees predictability. And while Noether provided this sweeping, elegant proof, experiments confirming this persistence have been conducted since Newton's time, moving through theories of caloric heat and the equivalence of heat and work.
So this isn't new.
Not at all. Every single observation, from the tiniest chemical reaction in a lab to the largest cosmological event observed by a telescope, reinforces the principle. Energy transformation is inevitable, but energy loss is impossible.
Now we have this immutable law in place, supported by math and centuries of observation. Let's apply it to our first big scenario: fire.
Let's do it.
The sources rightly point out that we often compare fire to life because it has such visible high exergy dynamism. Its sudden cessation feels like the ultimate loss of vitality.
It really does. But fire is fundamentally an exothermic oxidation reaction. When wood burns, we are watching stored chemical energy that's in the highly complex carbon-hydrogen bonds of cellulose being rapidly converted into low-complexity compounds.
Mainly carbon dioxide and water vapor.
Right. It's a process of simplification, and that simplification releases a lot of energy as light and heat.
Okay, let's look at the standard scenario first. A log burning completely down to ash in an open environment like a campfire.
In that open system, the chemical energy is fully converted. The heat radiates out, increasing the entropy of the surrounding air, the rocks, your face. The smoke, which is aerosolized carbon particulates, water vapor, and gases, disperses high into the atmosphere, carrying kinetic energy, which is motion, and potential energy, which is height.
And the ash.
The final ash is just mineral residue, chemically inert. It represents a near-zero energy state relative to the original fuel. Every single joule of energy has been accounted for and distributed into the environment.
But the sources wisely focus on the trickier scenario, the sudden cessation. What happens if we place a heavy, airtight glass bell or jar over a small, roaring flame cutting off the oxygen?
The bell trick.
The flame stops instantly. It's like magic.
This is the perfect test case for the LCE versus our perception. The visible mechanism. The flame ceases because you've removed one of the three legs of the fire triangle. Fuel, which is the wood, heat, which is the kindling, and the oxidant, oxygen. You stop the continuous chemical reaction.
But all that energy that was already released and the potential energy still locked in the superheated fuel, it has to go somewhere. It can't just vanish with the flame.
It can't. And if the energy doesn't belong to the flame, but to the universe, then the bell trick has to transform that unreleased potential energy in other ways.
So how does it do it?
Well, the crucial detail here, which addresses some of the ambiguity in the older ways of thinking about this, is that the system transitions from complete combustion to incomplete combustion and then stops entirely.
What does that mean, incomplete combustion?
Before the flame is fully extinguished, the rapid deprivation of oxygen causes the fuel to break down in a really complex way. Instead of cleanly turning carbon into CO2, it starts producing significant amounts of carbon monoxide, CO, and soot.
That's fascinating. So the fire doesn't just stop, it chokes. And as it chokes, it converts its remaining usable energy into two new forms of potential energy: a highly toxic gas and carbon particulates.
Exactly. Carbon monoxide is a flammable gas. It represents a chemically stored but unreleased form of exergy. When the bell stops the flame, the remaining energy is stored in a few places. The increased temperature of the air and the bell itself, the chemical bonds of that CO and the soot, and the superheated core of the wood.
So the energy conversion continues, it's just not a rapid, visible flame anymore.
Precisely. The energy continues to burn in non-visible forms within the closed system of the bell.
Okay, so can we break down physically where that energy is being stored inside that little suffocated system?
We can. We can break it down into three specific reservoirs. First, there's thermal energy, or residual heat. The bell and the air inside heat up significantly. This is latent heat transfer, where the molecules of the glass and the air are absorbing that energy and moving faster.
Got it. Reservoir 1, heat.
Reservoir 2, kinetic energy or vibration. The sources mentioned vibration. And this is the core mechanism of heat storage. The glass molecules and the air molecules are moving and oscillating violently, far more than the ambient room temperature. This movement, this increased molecular collision, never stops until the energy is dispersed.
Oh, everything under the bell is just humming with energy.
It's a dance of molecules. And finally, reservoir 3, chemical potential energy. That CO and the soot, they still retain potential energy. If you were to somehow remove the bell and immediately introduce a spark, the CO would ignite, releasing the rest of that stored energy as heat and light.
I see. So the energy isn't just waiting to escape, it's actively driving the molecular movement of everything enclosed, and it's remaining locked in these newly created chemical structures. The internal system has been violently driven away from equilibrium.
And that drive toward equilibrium is the ultimate fate of the conserved energy. When you finally remove that bill, the internal system is now drastically hotter and contains higher concentrations of chemically active gases like CO than the external environment.
So removing the bell acts like opening the floodgates for energy dispersal.
That is the perfect way to put it. Cold air rushes in, hot gases escape, and the residual heat, that thermal energy and vibration, flows out via convection, conduction, and radiation into the world. It flows until the internal system completely equalizes with the ambient room temperature.
The energy persists, but its concentration just fades away rapidly.
It's a critical concept for the listener to grasp. The law of conservation of energy, the first law, mandates that total energy remains constant. But the second law mandates that the usable portion of that energy, the exergy, must inevitably spread out and become useless energy.
The energy is conserved, but its highly organized state is lost forever to entropy.
The insight from this whole fire scenario is that the energy that constituted the visible fire is instantly and perfectly blended back into the universal inventory. It gets distributed across chemical bonds, the heat capacity of materials, and the kinetic motion of air molecules. It is the very definition of transformation and equalization.
That sets the stage perfectly for the most profound application of the LCE, applying it to the human body upon death.
The ultimate transformation.
We've established that the physics is non-negotiable, the energy must be conserved, but tracking the fate of the highly organized energy of a living being feels incredibly complicated.
It is complicated, but the LCE holds. A human body is a massive, complex, self-regulating chemical machine. It's powered by the concentrated chemical energy stored in millions of cells, primarily in the form of fats, proteins, carbohydrates, and of course the universal energy currency, ATP.
Adenosine triphosphate.
That's the one. When the heart stops, the complex metabolic system that maintains all that order stops, and the body begins its mandatory transformation.
What is the absolute first step of energy conversion after life ceases? It's often assumed that the body instantly starts cooling, which would imply energy loss, but that contradicts the LCE.
That's a great point. The initial phase is not cooling, it's actually internal self-destruction, which releases energy. We're talking about autolysis, which literally means self-digestion.
Self-digestion, how does that work?
Once the circulatory system stops, cells become deprived of oxygen. This leads to the breakdown of tiny organelle membranes within the cells called lysosomes. These lysosomes are like little bags of powerful digestive enzymes. When they rupture, they release those enzymes into the cell's cytoplasm.
So before external decomposers like bacteria even start their work, the body's own energy system turns on itself.
It does. The enzymes use their own stored chemical energy to begin breaking down complex molecules like proteins and nucleic acids into simpler components.
And this process releases heat, right?
Exactly. This is an exothermic process. In this initial stage, the concentrated chemical energy within the cells is being converted into simpler compounds and thermal energy. While the body eventually cools due to a lack of metabolic replacement heat, the initial process of autolysis is purely driven by the existing chemical energy budget.
So where does the majority of that concentrated chemical energy go in the immediate and short-term postmortem period?
The energy is transferred through two main vectors. First, significant amounts are released as heat, which radiates out into the immediate environment. This is the energy that contributes to the background heat of the room or the earth, increasing its overall entropy.
Okay, so there's the heat transfer. What's the second vector?
The second, and most important, is the biological redistribution phase. This is where the concentrated complex chemical energy becomes the fuel source for new life. This is where bacteria and fungi come in. They are the great decentralizers of the human energy infrastructure.
So they're taking over. How does that consumption process translate to energy conversion in the physics sense?
Well, these microbes perform cellular respiration. They consume the organic material, the fats, proteins, and sugars that are now being simplified by autolysis. And they use that chemical energy to fuel their own life processes: growth, reproduction, mobility.
So our energy becomes their energy.
Literally. And a significant amount of this consumption is aerobic, meaning it uses oxygen. This process produces large amounts of heat and CO2, carbon dioxide.
So the energy of the former individual is literally fueling millions of microscopic systems, and the byproducts are heating the environment and releasing carbon into the atmosphere.
And that's where the massive dispersal comes in. The carbon molecules that once formed complex brain cells or muscle tissues are oxidized and released as CO2. And this carbon dioxide is critical. It's now available in the atmosphere to be absorbed by plants through photosynthesis.
The sources really emphasize that the final state of the body is distribution. It's broken down into earth, water, and CO2. We're moving from a highly concentrated, incredibly complex energy state to a thoroughly decentralized one.
The sheer dispersal is the key to conservation. The elemental components, calcium from bones, nitrogen from proteins, carbon and hydrogen from everything else, become fully integrated into the soil and the atmosphere. The energy is never truly gone, it's just everywhere.
This leads to the very profound conceptualization offered in the sources. The individual is not gone, but rather rewritten.
I love that phrasing.
It suggests a physical permanence, not through retaining form, but through contributing to new physical systems.
It is the ultimate scientific definition of persistence. Your atoms and the energy stored within their bonds don't stop. They become part of the larger cosmic cycle. The nitrogen in your proteins might be taken up by the roots of a tree. The carbon is absorbed by grass. The thermal energy radiates off the planet and eventually out into space. You have simply transformed into the foundational components and the heat budget for the next iteration of the physical world.
That is a staggering thought, that the physics of conservation provides a very literal physical mechanism for persistence.
And this is why the sources draw that fascinating philosophical connection. Because of this undeniable mandatory cycling of energy and matter, some people connect the LCE, the sheer persistence of one's physical inventory, to the concept of reincarnation.
But not in a spiritual sense.
Not at all. It's not a spiritual soul that returns, but the actual atoms and energy that constituted your highly organized form, persisting and contributing to new growth, new systems, constantly cycling through the finite inventory of the universe.
It provides a grounded material answer to an age-old spiritual question. Your energy must return to the pool, ready to be utilized in whatever future configuration the universe demands.
It is physical, measurable, and absolute.
The LCE confirms that the energy of your life, however complex and individual, adheres to the same universal rules as a burning log. You are an energy system, and when that system ceases, the energy must transform and disperse, increasing the total entropy of the universe while maintaining the overall energy count.
It's the final accounting.
It's important to acknowledge that the curiosity that anchors this deep dive, that what happens when, question has obsessed humanity for millennia. Moving from that feeling of magic to observable fact was one of the greatest intellectual shifts in human history.
Indeed. The sources emphasize that establishing these conservation laws was the critical step that moved humanity past superstition. We stopped attributing phenomena like the sudden cooling of a body or a lightning storm to metaphysical forces, to demons or gods.
And started explaining them through quantifiable, predictable rules.
Right. And that shift required the scientific method, of course. But the philosophical groundwork was laid much, much earlier.
Let's connect the modern law back, 2,000 years, to the ancient Greek thinker Heraclitus.
Heraclitus famously encapsulated the concept of relentless transformation in his statement, "Everything flows," or panta. He was obsessed with change. He observed that you cannot step into the same river twice.
Not just because the water is different,
but because the whole structure of the system is in constant dynamic motion. While he lacked the mathematical language of conservation, he was articulating the underlying principle that the universe is defined by ceaseless movement and continuous energy exchange.
It's a really powerful philosophical precursor to the LCE. He didn't know about atoms or entropy, but he intuitively understood that the appearance of permanence, of a fixed identity, a fixed river, is an illusion built on constant underlying motion.
That ancient curiosity later fueled the technological revolution. We often think of these conservation laws as abstract, high-minded physics. But their rigorous definition was driven by a very dirty, very practical necessity in the 19th century.
We need to focus on the figures who industrialized the concept of heat transfer: Carnot, Clausius, and Boltzmann. Their work on thermodynamics literally defined energy usage for the modern world.
And their work wasn't just curiosity, it was direct engineering. The Industrial Revolution needed reliable, efficient engines. Specifically, the successful construction and optimization of the steam engine required engineers to precisely understand how much energy they could extract from burning a lump of coal.
And crucially, how much was unavoidably lost as waste heat.
Exactly. The need to maximize efficiency, to get the most work out of the fuel, forced them to define conservation rigorously. They needed to know the absolute maximum amount of work possible, which is defined by the LCE, and the absolute minimum amount of waste, that was defined by the second law, by entropy.
So who came first?
Sadi Carnot, in the early 19th century, was key. He focused on the cycle of heat engines, and he was the one who defined the theoretical maximum efficiency possible for any engine, what we now call the Carnot efficiency.
And he realized heat wasn't consumed.
That was his crucial insight. Heat was transferred. He realized that if heat could actually be consumed or destroyed, an engine could be 100% efficient, which he proved was impossible. His work provided the initial crucial insight that energy, in the form of heat, is conserved, even if its ability to do work is limited by temperature differentials.
Then we have Clausius, who formalized the concept of entropy, quantifying that drive toward dispersal we were talking about earlier.
Rudolf Clausius formalized both the first law, which is LCE, and the second law, which is entropy. He was the one who famously stated, "The energy of the universe is constant. The entropy of the universe tends to a maximum." He provided the mathematical language for why a concentrated form of energy, like the heat under our bell jar, must flow outward and become low-grade energy.
And finally, Boltzmann provided the microscopic, the atomic explanation for all of it.
Ludwig Boltzmann connected the macroscopic observation of heat, or temperature, to the microscopic movement of particles. He developed statistical mechanics, showing that entropy is simply a measure of disorder. It's the number of ways atoms and molecules can be arranged.
So a system with high exergy, like a focused laser beam or a living cell, has low entropy.
Very low entropy, very few possible arrangements. A system with high energy, like diffused heat or a pile of ash, has very high entropy. Billions of possible arrangements. He proves statistically that systems are overwhelmingly likely to move toward disorder, but the total energy of those moving disordered particles remains the same.
So we have this incredible scientific lineage, Carnot, figuring out how heat works for machines,
Clausius, formalizing the two great laws of conservation and dispersal.
and Boltzmann confirming those laws are driven by the simple statistical movement of atoms.
And all of that led to Einstein, who refined the picture even further with his famous equation EM's 222s.
Einstein didn't replace the LCE, he expanded it.
He expanded it into the law of conservation of mass energy. He showed that mass and energy are two sides of the same coin. They're interchangeable. You can convert matter into energy, like in a nuclear reaction, but the total combined quantity of mass and energy in a closed system remains conserved.
So he took the laws established by Noether and the 19th century pioneers and confirmed their universality, applying them not just to fire and bodies, but to the stars themselves.
The entire cosmos runs on this budget.
It's a history driven by intense practical necessity, which ultimately yielded profound philosophical comfort. The greatest thinkers, like Heraclitus and Noether, were those who just sat and wondered, what happens when? The exact same simple curiosity that drove our listener to share this stack of sources with us.
It all comes back to that simple question.
So we've concluded our deep dive by confirming that the questions surrounding endings, the extinguished fire, and the end of life are not mysterious at all. Their answers are deeply rooted in the fundamental physics of persistence.
The key realization is twofold, I think. First, the law of conservation of energy mandates that the total amount of energy never vanishes. It only transforms. And second, the second law of thermodynamics explains why this feels like loss to us. Because the useful energy, the exergy, rapidly transforms into useless, dispersed heat or energy.
That transformation ensures that whether energy is released as heat radiating into the environment, or kinetic energy sustaining molecular movement, or complex chemical energy being utilized by new life forms and dispersed as CO2.
The universe operates on a principle of perfect, relentless balance. Nothing is ever truly wasted. Everything is cycled.
We observed that these laws, proven mathematically by Emmy Noether and built upon by centuries of figures driven by both curiosity and the practical need to optimize the steam engine, govern every single moment of existence and transformation.
Which brings us to our final provocative thought for you, the listener. Something to mull over that builds on this physical truth. We know that everything you are, your highly organized energy and matter, will eventually fuel something new.
We know this as a fact.
It's a certainty. So given that certainty, and noting the mechanics of decomposition, what is the most beautiful way to conceptualize your energy being rewritten into the universe? If your energy is destined to become part of the wind, the kinetic motion in the earth, or the structure of a future tree, what physical iteration do you hope your persistence ultimately contributes to?
A heavy but absolutely grounded question. Thank you for joining us on the deep dive. Keep that curiosity flowing, just like the energy in the universe.